Okay, so we were looking at hardness, okay? And we have in MgO, the product of the charges is equal to 2 times 2, which is 4. But in NaF, the product of the charges is 1 times 1, which is equal to 1. And if you remember, the Coulombic attraction is equal to KQQ over R squared. So both charges are larger in MgO. And so that will make MgO harder. It will also mean that it has a higher melting point, and its lattice energy will be greater. Are we good with that? 88. Pardon me? QQ, good question. Sorry, yes. Charge times charge. Q1 times Q2. Yeah? So in MgO, we have a 2 plus charge and a 2 minus charge. And in fluorine, we have a 1 and a 1. So if we ignore the signs on those, we have a 4 and 1. Okay? Yeah. Okay. So let's move on to page 88. Or sorry, 89. Solubility. What do you think happens to solubility with lattice energy? As lattice energy increases, solubility decreases. So the higher the lattice energy, the less soluble. Dissolving can actually be broken into 2 steps. I think it's 2 steps. Well, kind of. So we break apart the solid and we split them into gaseous ions. Now, in reality, this is not what happens, but thermodynamically, you can think of it this way, okay? So if we were to take all of our crystal lattice and split it in, there would be a delta H, and it would be equal to the lattice energy. And because we're breaking it apart, in this case, it would be positive or negative. Bond breaking, delta H would be positive. Thank you. Okay. Now, to be honest, there's actually, I'm going to say there's a step 1B as well. You also have to split apart the solvent molecules. You have to make space between the solvent molecules. Yes.
What is delta H cycle?
Change in enthalpy. So molecules split apart, the solvent molecules to make space for the ions. So if you have water, the water actually needs to break apart. So this will also have a delta H. And is this delta H positive or is it negative? Well, we're splitting apart the solvent, so we're taking a water and a water that are next to each other, and we're moving them apart. Is that endothermic or is that exothermic? Endothermic. What are we breaking? The solvent-solvent IMFs. I don't know why that B is so weird. Irritates me. Let's fix it. What if it was water? Let's say it was water. What kind of IMFs would we be breaking? Dipole, dipole, yes. Anything else? H2O contains dipole, dipole. What else? Hydrogen bonding. Dipole, dipole. Hydrogen bonding. Anything else? Everybody, all molecules, all have LDFs. Okay, so if you're like, what are the intermolecular forces present in water? If you have hydrogen bonding, you also have dipole-dipole, okay? And everything always has London dispersion forces, okay? So it's like, if you have dipole-dipole, you will also have London dispersion. If you have hydrogen bonding, you'll have hydrogen bonding, dipole-dipole, and London dispersion forces. Okay, so it kind of goes. Which of those would be the most important in water? Which would affect, like, say, the boiling point of water the most? Which are the strongest? Yeah, the H bonds are the most important. Okay. And then once we've had an endothermic process, splitting apart the crystal lattice, an endothermic process, splitting apart the solvent molecules, we can then have the hydration process where the water, say, surrounds the ions. Yes? And we get, what do we call this little circle of ions here? That's called a hydration sphere. What kind of IMFs have formed here? Ion dipole. This is a very strong IMF. For an IMF, it's very strong. That's why it can compete with the ionic bonds. Okay, so here's our ion dipole. And so delta H of hydration, is that positive or is that negative? It's going to be negative. Why is it negative? Have a chat about that with your neighbor. Why is it negative? The ion dipole forces are forming. They form. And if they form, it is exo. Okay? And so what you would do in order to find the overall enthalpy of the dissolving process is you would take, let's call this one delta H1, delta H2, and delta H3. So we have delta H of the lattice energy. Let's grab this. Whoops. And then we have the breaking apart of solvent, breaking apart of solute. Break the solvent, or sorry, break the solute, break the solvent. Break solvent. And then put them together. Yes. And then down here, we have solute plus solvent go together. And so delta H of dissolving is going to equal delta H1 plus delta H2 plus delta H3. Yes? You'll get more introduction to this whole thing over summer, because summer is going to be some more thermochem, okay? But I did want to introduce it to you here because it can help you think about, well, I need to have, in order for this to be favorable, which one's favorable, endothermic or exothermic? Do things like to go to a higher energy or do they like to go to a lower energy? They like to go to a lower energy. So in order to go to a lower energy, we need this one, which is the negative one, right? The formation of the solute-solvent bonds. We need that to be big enough to make the whole thing a little bit negative. Yeah? Now, of course, there's another factor as well, and that's the fact that the universe also likes things to become more random. What's more random? A salt crystal sitting in water or a dissolved salt crystal with all the little ions all moving separately? Which one's more random? The dissolved one. So it's not like if you have a positive value for dissolving, it still might dissolve as long as the randomness is sufficiently increasing. But again, that's going to be for next year. So don't worry about that too much. Okay? Because if you're all looking at me like you are right now, like, what did she just say? We're going to move on. Okay? This one doesn't include the delta H of breaking the IMFs, the solvent IMFs. I need to fix this graph here. So if we're asking ourselves, will an ionic salt dissolve in water? If we have a pair of oppositely charged gaseous ions that are placed together, they attract each other. That's our lattice energy. If we put those ions in water, that's our hydration enthalpy. And you can essentially, I guess because intermolecular forces are so small compared, the greater the lattice enthalpy, like if your hydration enthalpy is bigger, it's going to be more soluble. So basically, if you have a larger lattice, all I'm trying to say is if you have a larger lattice energy, it won't be as soluble. Okay? Which is a long way of saying what we said right at the very beginning. Yes? Larger lattice energy, less soluble. I feel like I've added way too many words and concepts to this. Does that statement make sense? Yeah? Okay, cool. That's really all you really need to know. Okay? Larger lattice enthalpy or energy, less soluble. Okay, blah, 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 blah. Okay, let's see. Enthalpy change, blah, 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 blah. I obviously got really carried away with this. So let's just skip past that. And there, we're done with that. All right. Metallic bonding. And if you were in grade 9 with me, you probably saw this last year just before Christmas. So, shall we watch the little video here? Okay. Let's see. Do I have my sound on? My sound is on. That's good. Is it on all the way? Yes, it is. Good. Okay. Okay. So just before we go on, a sea of electrons, all my grade 9s, when I said a sea of electrons, even though it was written SEA, they all wrote C when they had to, but it's not a sea of electrons, it's an SEA of electrons, like an ocean of electrons. What's the problem with that if they're all positively charged? Yeah, plus, if I have a metal, like if I have silver, are the atoms actually positively charged when it's just silver? No. So this particular model, the way it's shown here, is not yet complete. Okay, there's something missing. Okay, so 13 protons, 11 electrons, 10 electrons. So what is the overall charge? 3 positive. Where are the other electrons? So those electrons are not tightly held to the cation, okay? And that's because metals are not very what?
Electronegative.
Electronegative. So they're not really good at pulling electrons towards them. So the aluminum's like, oh, here I'm an aluminum and there's an aluminum over here. Here's my valence electron. But I'm okay if you take my valence electron and I grab one from over here. Okay, so the valence electrons are free moving. They are what we call delocalized. Have we used the word delocalized before? Yes, we have. And in metals, the electrons are delocalized. The valence electrons specifically. And this is my ever so sophisticated model of metallic bonding. In here, in this little plastic container, I've got styrofoam balls. What do the styrofoam balls represent in this? They represent the cations. Yes? And you can see there's bubbles in here because I didn't get all the air out. What's in between them is actually corn syrup. And if anyone wants to get really like weirded out by this, I've had this model for at least 10 years. Corn syrup, because it's got so much sugar in it, it won't go bad. Okay, that concentration of sugar will just stay fine. And it's never been opened. It's styrofoam balls in corn syrup. Because I wanted something gooey, something sticky, right, that I could put in here. Yeah, so that sticky, gooey corn syrup represents, what does it represent? The sea of valence electrons. And those electrons, if we tilt this like this, maybe the bubble will move. It's not as mobile as it used to be because it's been sitting around and I think a little bit of it's dehydrated a little bit. But if you wait, you can actually see, it's moving a little bit. Okay. So it is holding those together. You can imagine the cations are repelling each other, but all in between. It's like there's like liquid glue in between everything holding it sticky together. Yeah? And one of the things about this model, can you imagine, now I cannot open this because styrofoam is much less dense. So this model is imperfect and all the styrofoam would come up out of the corn syrup. Okay, so corn syrup and styrofoam balls, not the best model. But let's say I had something that wouldn't pop out. And if I could open this, what would happen if I pushed down on it? It would just move out, right? But they would still be stuck together because there would still be corn syrup in between them. And that's like what happens if you hit a metal with a hammer. It doesn't break. It just moves out of the way. Yeah? And if I were to, take one end of this, let's say it wasn't sticking to my hands. If I took one end of it and the other end of it and I grabbed it and I pulled it apart, it would just kind of get longer and longer and longer. And finally it would just break because there was just a small stretch of it. Does that make sense? Kind of like dough. If you take dough and you stretch it, it just kind of stretches and then eventually it gets small enough that it'll break. That's why metals are both malleable. Do you guys remember the word malleable? Okay, that means if you hit it with a hammer, it will deform. It will not break. It is not brittle. Okay, and it is, what's the other word? Pulled into wires. It is ductile, yes.
Oh my goodness.
Okay, and this is also an important concept. I don't know if I actually put this particular animation in your book, but this is important to know. If I haven't, I'll make a copy of this picture and show it and get it to you, okay? All right, so we've just hit it with a hammer, and I'd like you to look at this plane right here. What's going to happen between this half and this half? They're going to repel each other. Yeah? That's why ionic crystals are brittle, because all of a sudden, if you shift it, instead of being beside things that attract, those ions are going to be beside things that repel. So ionic crystals are brittle, whereas metals are malleable. So if you have more delocalized electrons, that will make the metal harder. Yes? Okay, I want you to think back to before Christmas when we took the sodium, and what did we do with it before we put it in the water? We cut it. How hard is sodium? It's pretty soft, yeah? Right? If you can cut it with a knife, it's pretty soft. How many valence electrons does sodium have? Just one. So sodium is only giving up one of its electrons to the sea of electrons, but aluminum gives up 3 electrons. So aluminum is much harder. And I don't know if you've ever like seen like a block of aluminum, but like they'll make bicycles out of aluminum. The bike frame is made out of aluminum. Yes? And if you were to like try and cut through that with a knife, how well would that go for you?
No.
Not very well, okay? Because aluminum is much harder because it's got a greater sea of electrons holding those atoms together. Ooh, titanium, 4+, 4 electrons, very tough. That's why you'll see things made of titanium and they're just very, very hard, okay? And same thing with molybdenum, very, very hard. How does this model explain electric current? I want you to think about that. What if I put a positive charged plate over here and a negative charged plate over here? What would happen to those moving electrons? Positive is over here, negative is over here. They're all going to move from negative, away from negative and towards positive. So that's why it conducts. According to this little animation, which side has the positive plate on it? Where is the positive plate? Over there? Over there?
Why does
The electrons are going, which way are the electrons going? They are going to the left. And so the positive would be on the left. Yes. Sorry, I have to like backwards myself, right? Because I'm looking at it this way and I have to, anyway, so thank you for helping me with that. You're never going to have to explain that one, okay? But it does. The sea of electrons also explains lustrousness, but you will never have to like write an explanation about that. I have never seen it in AP, okay? Never. Why are we doing this so slowly? Oh my God. Are we done? Did that make some kind of sense? It doesn't need to make a lot of sense. It just needs to make a little bit of sense. Did that make a little bit of sense at least? Yeah? Okay. Okay, and I think that's it. Yes. Did we like that video? Informational? I liked it. Okay, so I don't think we actually need to go through this because it's mostly just a written form of what the video went through. You feel free to read it on your own. Okay, blah-de-blah-de-blah. Malleable. Ductile, just here's another picture of something being malleable. And ductile is if you force a metal down through what they call a die, which is just something very hard. If you push copper, say this maybe was made of, this die might be made of molybdenum, which is much harder than copper because copper has 2 valence electrons and molybdenum has 6 valence electrons. So if you push on this metal rod and it goes through a large hole, it can actually get squeezed out into a smaller hole, and you can see that happen like that. Like this will get squashed out into a single stream of the cations. Well, probably not a single row, but less. Lustrous, blah-de-blah-de-blah, good conductor of heat. They're also a good conductor of heat because those electrons are mobile. They can quickly pass. What is heat anyway? Heat is essentially energy, okay? The kinetic energy gets passed along. This is on page 98. Yeah? Whereas if you had something like, I don't know, so you had an ice cube, yeah? An ice cube actually takes a fair bit of heat to get the particle, to get the energy to go from here to here. That's why, you can have the surface of the ice melting, but, if you've got a lake, if you have 6 inches of ice, it's going to take a while for the lower levels to start melting because it takes a lot more time for it to move. Because if you have a water crystal, so if we have our water crystal like this, you're going to have every H2O, it'll be jiggling. They'll all be jiggling, yes? But nobody is going like this, bam, and pushing the next one along. In the metal, the electrons can actually physically move. That's just called translational motion when they move through space, as opposed to vibrating or rotating. Okay? Water molecules can only vibrate when they're in solid form, whereas in a metal, the electrons within the metal can actually translate. Translational motion. Okay? Vibrational motion, translational motion, rotational motion. Also vibration. Okay? But the fact that the electrons have translational motion means that heat can be passed along faster. Okay, what else did we have in here? Anything else? Good conductor, blah-de-blah-de-blah. Strength of metallic bonds, we talked about that already. Group 1, less strong than group 2. Does it make sense that the metallic bonding in group 1 is less strong than in group 2? This is page 99. Yeah, this is gonna the group 2 will be harder and it'll have stronger metallic bonds. Okay, that's what they were talking about in the video. Okay, there's some exercises here. We're not going to do those. We're going to move on to alloys. Woo! Let's keep going. Because metals, this is on page 103. Have you guys heard of alloys? Yes? Do you know what alloys are? They are metals with other, usually metals, but sometimes non-metals mixed in. Okay? So stainless steel is an alloy. Stainless steel is made of iron plus carbon, usually plus chromium. Sometimes there's a little nickel. Okay? And how do we make an alloy? We melt. Say we wanted to make a silver gold alloy. We would melt the gold, melt the silver, mix them together, and let it solidify. Yeah? So 14 karat gold is an alloy. Okay, you can make it into rose gold by putting in more copper. You can make it white gold by putting in more platinum. Okay, so gold can be different colors depending on what you alloy it with. Okay, and it will have different hardnesses depending on what you alloy it with. Anyone have anything made out of 24 karat gold? No, what's wrong with 24 karat gold if you wanted to make like a piece of jewelry out of it or whatever? It's pretty soft, okay? Gold is pretty soft. You can harden it by adding in other metals, and we're going to look at why that works, okay? Because metals consist of a lattice of cations surrounded by a sea of valence electrons, do they have to combine in any particular ratio? Or could I just melt 50% silver, 50% gold, swirl them together, let them harden? Can I do that? Could I do it with a 90-10 mixture? Absolutely. So alloys are not compounds because compounds have specific ratios, whereas alloys are mixtures. They are homogeneous mixtures of solids. Yeah. Yeah, exactly. Okay. So they're homogeneous mixtures of usually metals or sometimes nonmetals.
Wait, what?
Sometimes we can throw in a nonmetal like carbon and steel, or plus a nonmetal. Yeah. Sorry? Yeah, alloying something is a physical change. Yeah. So there's no need for any particular ratio. See, these are not compounds because compounds, oh, it does say it here. In a compound, the ratio is always the same. It is always consistent. The ratio in alloys can be different. So they're not considered pure substances, they're mixtures. So if we look at our pure metal, which is the red metal, or the larger dots, we could have a ratio of 22 to 8. Okay?
Where's one of these represent like an atom?
Yeah, each of these is an atom. Or actually, it's a cation in a sea of valence electrons. So we have a larger metal and we have alloyed it with a smaller metal. And we could have alloy 1, which has more A. We could have it where it's a 50-50 mix. That's a different alloy. We could have a 1-to-2 mix. You could have any mix or any other ratio. Yes, so alloys can have any percent. Two metals melt, mix, let harden, that's an alloy. Now, why would we do this? Why do we bother with stainless steel? Why don't we just use iron? Because it rusts. Yes. So by putting some chromium into our steel, the chromium actually forms chromium oxide on the surface. And chromium oxide is very, very hard, and it prevents the oxidization of the iron. Iron oxide makes a crusty, yucky, yeah? Iron oxide is crusty and yucky and red and flaky, and like it just destroys the structural integrity. Whereas chromium, when it oxidizes, provides a smooth layer that's just there. Aluminum also does that. Yeah. Okay. It has carbon and chromium. Now, steel by definition has carbon in it, carbon steel, I think. I could be wrong. But I think it's you can have non-stainless steel with carbon in it. Okay? Yeah. They can also have nonmetals. Okay? I'm not quite sure how they get them in there, but I assume like they maybe took some ash, like back in the day, obviously they made like steel back in the day. They would take some ash or something like that and make it really small and then throw it in the pot with everything else and then let it harden. Okay? I'm sure you could look up, like, somebody's got a video out these days now, you know, of somebody making steel from scratch from iron and carbon, right? Okay, so alloys always involve random mixing. So if you're looking at an alloy, do you see how these guys are randomly distributed?
So it's not even.
It is even, but random. Randomly and evenly distributed. If you were to go to a bigger section, it would all look the same. When you focus down small, it looks like it's different in different areas. But if you back out to a much larger perspective, you'll be like, on average, it is all the same everywhere, right?
Yeah.
Now, ionic compounds, I have a feeling that if they give you an ionic compound in the AP exam, they're going to put pluses and minuses on there. Okay? Which will let you know that it's an ionic compound. These are alloys. You'll notice that this has pluses and minuses, and they are alternating regularly. So if you have alternation in a regular pattern, that's going to be ionic. I don't think they're ever going to give you anything that's not a one-to-one. But if they do, can you see that the one on the right is also a regular pattern? Do you see the regular pattern? But I don't think they're going to give you that. And if they did, I think they'd be like kind to you and they'd be like 2 plus, or sorry, 2 minus. Plus, plus, 2 minus, plus, plus. And you'd be like, oh, that's an ionic compound, not an alloy. Yeah? But like I said, I don't think they're going to give you anything that complicated. I think they're going to be like, let's give them a really nice 1-to-1 ratio ionic compound to look at. And if they do give you that, I think they're going to put charges on those. So if we don't have charges on them, like let's say we looked at this, is this an orderly arrangement? Is this regular? Yeah. And that way, if I was not given charges, I would guess it was ionic compound, because the ratio is always the same. And I can't change the ratio. How about the next one? Is it orderly? Yes. So I would say not an alloy. That's probably an ionic compound. But like I said, I'm guessing that whoever's doing that, they'd stick some nice charges on here for you. You know what I mean? Right? I think that's going to happen. And this one obviously is ionic because it is regular. If we go back to our alloys, up at the top of the page, irregular. We good with that? Let's see what else we got here. Ooh, now we have 2 types of alloys. Interstitial. What does inter mean? Between. So if you were to look at, if they weren't labeled, if you were to look at this alloy and this alloy, which one would you think is interstitial? The first one, because those little things are in between. Yes? You got things in between. The carbon slots itself in between.
Wait, did those just have to be non-metals?
It could be a very much smaller metal, but often interstitial ones will be nonmetals because the nonmetals tend to be smaller. Yeah? What do you think this would do to the hardness of iron? It strengthens it. So if you imagine you're hitting it with a hammer, okay? If you just have these guys, they slide across each other quite nicely, okay? There's a little bit of bumpiness, you know, so they bump along, yeah? But if you put in something extra, it's like an extra speed bump. Okay? So if you're hitting it with a hammer, it's like, it's got to like kind of get over that little extra bump. Yeah? So one of the reasons we alloy things is to make it harder. They make the sliding of layers more difficult. You're also going to end up with an increase in density. Can you see why this would increase the density?
No volume change, but yes.
We got more stuff within the same volume. Yeah? It's going to increase the total attractive forces because there are going to be new attractions made to the smaller atom, while the attractive forces among the larger atoms are only slightly disrupted. So it is usually going to be stronger and harder. Okay? You're not going to have to describe why. Normally, you're just going to be like, alloys are stronger and harder. So that is, what did we call those kind of? Oh, here we've got some Latin. Interstitial. Stitial comes from sistere, which means to stand. Okay? So interstitial means to stand between. Anyone taken biology and learned about interstitial things? You'll come across the word interstitial in biology as well if you take Bio 12, I think. Okay? Yeah. Okay, substitutional alloy. So instead of sticking things in little spaces in between, what do? We substitute something of similar size, right? So instead of just having purple, 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 we'll have purple, blue, purple, purple, purple. Okay? It should be similar size so it can fit within the same matrix.
So there's the sign instead.
And what's it doing? It's substituting in. That's why it's called substitutional. I don't think they're going to make you pull those words out of your ear. I was going to say something else, but out of your ear works. I don't think they're going to make you take those words and pull them out. I think it would be in a multiple choice question or in the question itself, it would use the word interstitial and substitutional so that you don't have to be like, can I spell? It was inter something. I cannot remember. I think the word will be there for you. Okay, but you will need to know what it means. They don't come up a lot. Alloy questions don't come up a whole lot, but they do from time to time. So if you're like, oh, I didn't learn about alloys, you might maybe lose 1 mark. Do you know what I mean? Not a lot. Substitutional alloys replace one set of attractive forces with an almost identical set of attractive forces from the added metal. You can get it to be harder if you add in something that has more valence electrons. you usually end up with properties somewhere in between the two metals. So that's why rose gold, which has copper in it, has that sort of rosy hue from the copper, right? It's a little bit harder because copper is harder than gold. Many pure metals are too soft for many uses. Adding another element makes it harder. They're generally stronger and harder. Here is an example of the speed bump effect. If we put a force on this layer here, it will force that along, and you can see it just slides without too much difficulty. But if we put a force here, what's going to happen when this one tries to move? It's going to be like, right? Have I lost you all entirely? Has it been too long of a week? What's going to happen when this one tries to slide? It's all going to move, but is it going to move as easily as this one?
No.
These all just kind of slide, whereas this one kind of has to go, right? It has to kind of bump over into the next one. Yes? Okay. Heat resistance. You get more heat resistance. I don't know. There's some work stuff there. Does anybody want the Unit 12 book over the weekend? If you would like the Unit 12 book over the weekend, you can come and get yourself one. I think some people have done it already. You get yourself one of these. Go in here, you get yourself a duotang. You put it in the duotang and you get yourself a answer key. Okay? There are many other duotangs here.
No, I go home. I can play it like that.
Yes.
No, I think you like,
See, where did I put them? I think they are right here. And if anyone wants to take the molecular geometry quiz again, I've got those. Where no. You guys can either sit apart or put up a divider. Yeah. Yeah. That's okay. I can get you another one for next week. Yes. Yeah. A lot of the stuff in Unit 12 is review. Good news. And we might not get through it all. We'll see how far we go. Hi.
So I just wanted to double check.
Yeah.
This
Mhm.
would be like 90 because there's two.
That because and
Like
they balance the
balance it
forces
out,
balance
yeah.
each other. That's
So it'd be the
perfect.
same as
Exactly.
the one.
Exactly.
Okay,
Yeah.
perfect.
Yeah.
Could I retake it again?
Absolutely. I'll have one ready for Monday. Okay. Yeah. Might as well get perfect. Why not?
Yeah, like I know it.
Yeah.
A little bit.
Yeah.
This kid already. This man was a movie like